Okay, today we're going to talk about relationships in equations and mole ratios and limiting reactants. So first off, a chemical equation is what describes what happens in a chemical reaction. They will always follow the law of conservation of mass. That is to say that the same number of atoms that are reactants will equal the same number of atoms that are products, right? Mass is conserved. So to write an equation, we're going to identify all the reactants and all the products. And so generally your reactants will be written on the left side, whether there's one, whether there's two, doesn't matter. And the products will be on the right side, again, 1, 2, 3, however many. And we will draw an arrow to signify the change, right? So everything to the left of the arrow is reactants, everything to the right of the arrow is products. Now, physical states will generally be indicated, right? So S for liquid, S for solid, L for liquid. AQ means aqueous. Aqueous. Aqueous means dissolved in water. We're going to talk a lot about that next unit, solutions. For right now, at the very moment, I'm not totally concerned with states of matter. I'm more so concerned with your balancing and your mole ratios. There's one simple rule for balancing an equation, and that's that you can only change coefficients. Change coefficients. You cannot change the subscripts because changing subscripts would be changing the formulas. And you cannot change formulas when you balance because you're changing the identity of what you're saying that you have, right? So in other words, you can only change the multiples, right? And there's no one method to balance the equations. Generally, it's trial and error. I look for the most complicated molecules first and work from there. So example, sodium sulfate solution, barium chloride solution are mixed to produce barium sulfate and sodium chloride. All right. So I need to look at the charges on these so that I can write the formulas correctly. Sulfate I know is a -2, sodium is a +1, barium is a +2, chloride is a -1. So let's start off by writing our reactants. So the formula for sodium sulfate would look like this. They do tell me that these are both solutions, which means they are both aqueous. Barium chloride, barium's a +2, chlorine's -1, so it's BaCl2. Again, aqueous solution. Draw an arrow. Now, right now, we didn't go over how to predict what... Actually, we're not predicting anything. They tell us what the products are. Barium sulfate and sodium chloride. Okay, now we've got to balance this. So, the most complicated formula, the biggest looking formula, I mean, this is kind of arbitrary, but I would say it's sodium sulfate. And there's a 2 on the sodium. So since we have 2 sodiums on the left, we need 2 sodiums on the right. We can achieve that by multiplying sodium chloride by 2. Right? I just wrote in the coefficient of 2, so I can only change coefficients. All right, now that I have a 2 in front of chlorine or sodium chloride, I need 2 chlorines on the left side, and they happen to already be there. And now there's 1 barium and 1 barium. So now we're done. That's that equation balanced. I guess if we really want to finish it off, we would say that this is a solid, and this is still aqueous, but I wouldn't expect you to know that yet because we need to go over solubility rules for you to know that. All right, let's try the next one. Propane gas. Like propane as in your gas grill, what you buy in front of Menards and tanks, right? It's propane. Burns in oxygen. So burns in oxygen is another way of saying reacts with oxygen. Oxygen is a gas. Propane is a gas. Those are my 2 reactants. Carbon dioxide is formed and water vapor. Technically, it's formed as a liquid first and then turns to vapor, so I'm just going to put an L there. Again, I wouldn't expect you to know that right now, but we're just putting an L there. Write a balanced equation. Okay, so most complicated formula, to me, I'd say here it's C3H8. This is classically what we call combustion because I see a hydrocarbon. That's a hydrocarbon. Whenever you see hydrocarbons reacting with oxygen, that's a telltale sign that it's combustion. Okay, so if it's combustion, there's an order that you should follow to make this easier. The order is C, then H, then O. So carbons first. All right, so I'll put a 3 in front of the CO2. That fixes my number of carbons on both sides. Now if I have 8 hydrogens on the left, what could I put in front of water to achieve 8 hydrogens? 4. All right, so oxygen is left to be last. And this is good because any element that appears more than twice, you want to leave that to the end and let it be figured out by the other balancing. So I've got a total of 10 oxygen atoms on the right side. Everyone see that? 3 times 2 plus the 4. Okay, so I need 10 oxygen atoms on the left. We can achieve that by putting a 5 here. And now we are balanced. Okay, trial and error. Start with the most complicated. Okay, you guys are pretty good at balancing, so we don't need to belabor that. Okay, mole ratios. Coefficients in balanced equations show the mole relationships between various reactants and products. So we see from this equation they're referring to the one we just balanced, right? 5 moles of oxygen are needed to burn 1 mole of propane and to produce 3 moles of CO2 and 4 moles of water. Okay, so whenever I refer to 2 species in an equation, I can do so using a mole ratio. 1 mole of propane to 5 moles of oxygen. This mole ratio is kind of the key to doing any kind of stoichiometric work in balanced equations. You have to understand how to find the mole ratios between any one of these. So there's mole ratios between water and CO2. There's mole ratios between water and O2. There's mole ratios between CO2 and propane. Any 2 things in a balanced equation will have a mole ratio. You just have to refer to the coefficients that are being used. All right, so if 1.65 moles of propane are burned in excess oxygen, how many moles and how many grams of carbon dioxide will be produced? Okay, so stoichiometry work in a nutshell is dimensional analysis. If you line up and cancel your units properly, then you are doing stoichiometry. They are asking for CO2. So I'm going to put the moles of CO2 in the numerator, and the number that I use is from the balanced equation. My coefficient for CO2 is 3. 3 moles of CO2. The coefficient for propane was 1. So as we see from our cancellation of units, all I need to do is multiply 1.65 times 3. Okay, a 1-step mole ratio problem. Now they also asked for mass. They wanted grams. So when you want to convert this to grams, you're just going to be multiplying by the molar mass. So 1 mole of CO2 would weigh 44.01 grams. And we got 217.8495. We'll go with 218. Make sense? Change from 1 mole to some other mole using a mole ratio. And then here, lastly, convert to mass. Okay. So, as long as you have a balanced equation, you can solve for anything. How many moles of water will be produced by burning 20 grams of propane? So 20 grams C3H8. What will my first step here be? Yes. Guys, whenever you see grams, grams are great, but grams cannot get you through a stoichiometry problem alone. You have to convert them to moles. The universal unit is moles. So propane's molar mass, let's add that up real quick. 12.01 times 3 plus 6. All right. 8. Okay, the molar mass we're looking at is 44.11 grams. That is our first step. I'm going to write an answer with an extra sig fig just to carry it through so that I don't get drift with rounding. So that's how many moles of C3H8. And then we can convert how many moles of water were there. According to our mole ratio, there's 4 moles of water for every 1 mole of propane. Okay, so 1.813, 4-ish moles, and we want to express an answer here, so we originally had 3 sig figs, so we're going to go 1.81. We didn't ask for water. If they ask for water, we, of course, can go one more step and convert to water. Okay. We don't need to do all of these examples if you guys are okay with this, right? Converting from moles to grams, grams to moles. Okay? All right. So, the main idea for the day is limiting reactants' theoretical yields. We may get to excess reactants today, we may not, I don't know, we'll see. Okay. In any chemical reaction, one of the reactants will limit the amount of product, right? In anything, if you're making anything, something runs out first. That's the limiting reactant. If you're making chocolate chip cookies and you've got bags and bags of flour and sugar and you have all the butter, but you only have 1 package of chocolate chip cookies, that's going to run out first, right? This is the same thing with chemical reactants. So in any situation, we need to figure out what is the limiting reactant. If we understand there's a limiting reactant, then we also understand there's a limit to how much product can be made. All right? So the best way to learn this is to jump right in. Here I have a balanced equation. This tells me that 2 moles of silver react with 1 mole of iodine to form 2 moles of silver iodide. Now, a little aside before we get too far in here. Everyone see the subscript here? Okay? This is one of the diatomic elements. There are 7 diatomic elements. And what this means is when these elements are alone, they always exist with a subscript of 2. They exist in pairs. They are hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. Now you can remember these 7 if you just remember the acronym Hunkelbrief. Hunkelbrief. All 7 Hunkelbrief elements exist diatomically, but only when alone. When I say alone, I mean not bonded to other elements. Right? So here we see I2. I2 is alone. It's not bonded to any other elements. That's why it has a subscript of 2. But notice the subscript on I is not 2 on the product side. Okay? The subscript does not have to be 2 because it's bonded. All right. Find the limiting reactant. Here we have a problem, and we're starting with, we're going to skip this one. We're just going to jump in with the grams. We have 1 gram of each reactant. As we mentioned earlier, every time you start with mass, you must convert to moles first. So 1 gram of silver, molar mass of silver, 107.9. Zero 0.009268, we'll call it. Okay. Moles of iodine. We got 1 gram of I2. Because it is diatomic, that means you take your molar mass twice. So 126.9 times 2, 253.8 grams. Okay, we've got moles of both reactants. Now, your next step is to figure out, all right, which product that I'm going to be solving for. In this case, there is only one product, so the choice should be clear. But sometimes there's more than one product, right? And I'll talk about that in the next problem. I think that'll present itself naturally. Okay, so let's solve for the product. 2 moles of AgI formed for every 2 moles of Ag consumed. Okay, so the numbers cancel, so your moles actually ends up being the same number. We do it again for the second element. 2 moles of AgI will be produced for every 1 mole of iodine consumed. Okay. We have 2 numbers that we just wrote down. Only one of them can be correct. From the silver perspective, 0.0092 moles can be made. From the iodine perspective, 0.0078. All right. So which one is correct? How do we know what the actual amount that will be made will be? It's going to be the lower. It's going to be the lower. The lower value, and we have a name for this. We call this the theoretical yield. The other value is fictional. That can't happen. And of course, if this is asked for in mass, then you just go one more step and you convert that moles into grams. But this is basically your steps. Convert your mass to moles, use the mole ratio, solve for the product, decide of the values which one is the theoretical yield that's going to be the lower. What if there were 3 reactants? How would this problem change? If I had 3 reactants coming together, would that make any difference? It wouldn't. You'd have a little bit more work to do. You would conclude with 3 numbers, but you still choose the lowest one. Okay? All right. This example here is basically the same as what we just did. So I'm going to skip over that one so that we can talk a little bit about excess reactant and do one of those. Okay. Oh, wait, actually, I'm getting ahead of myself. I forgot to do one thing. Once we determine the theoretical yield, guys, we also have to determine something else. Which reactant ran out first? It's the one that produced the smaller yield. The limiting reactant was iodine, yes. Okay, the limiting reactant produced the smaller yield, i.e. ran out first. Okay. These 2 things, the limiting reactant and the theoretical yield, will be found in the same line of work. So, if there are 2 reactants and we just identified the limiting reactant, the other reactant, the silver, has a name also. This is what's called the excess reactant, because there's some left over. So, if we had 3 reactants, we would have 1 limiting reactant and we would have 2 excess reactants. Okay? All right. So there's a excess reactant. Once we have gone through a problem and we have calculated the limiting reactant, the theoretical yield, oftentimes we also need to calculate how much of the excess reactant was unused. So to do this, this is like the tail end after a limiting reactant problem, right? So whenever there's an excess reactant problem, that means you're doing the whole problem plus some. So let's just do a problem and I'll explain the steps as we go through it. So they want us to find the excess reactant for the silver and iodine problem above. That problem was here, the 55 and the 31. So let's do that. 55.00 grams of silver and 31.55 grams of iodine. Okay. As before, first step, convert to moles. Okay. Next step, solve for the products. And our balance equation tells us that there were 2 moles of AgI for every 2 moles of silver. Therefore, the number is unchanged. It was 1 mole of iodine in the equation. Okay, again, we get 2 yields, right? Now that I have both terms in like units, now is the only time they can be compared. All right, you can only compare like units. So these are both in moles of, oh shoot, I wrote that wrong. That's not I2, that's AgI. Now that I wrote them both in AgI, moles, now I can compare them. What is my limiting reactant? It is iodine again. My theoretical yield is given. Typically, theoretical yields in lab problems need to be expressed in grams. So we'll go one more step. We'll convert this to grams. So molar mass is 234.8 grams. Okay, so 55.13 grams. That is our theoretical yield. Okay, so far, this is a limiting reactant problem, just like the one that we did. Now, we need to know how much excess reactant is left over. So here's how you do that. Start with the theoretical yield in moles. Use mole ratio to solve for excess reactant used. And then lastly, subtract ER moles used from ER moles initial. Okay. So, theoretical yield was 0.2486. So, and notice I'm saying start with the theoretical yield in moles, not the grams, right? Start with the moles version. So, 0.24862 moles of AgI. Mole ratio, solve for the silver. So 2 moles of Ag for every 2 moles of AgI gives us the same number, 0.24862 moles of Ag used. I am changing the label because what this tells us, we're figuring out how much of the silver was used because we know what the amount of products that can be made is. So that's used. Now I need to look through my work. How many moles of silver did I have initially? It's on there. Yeah, it was one of the first things we calculated. So we're just going to subtract. So 0.50973 moles of Ag initial minus 0.24862 moles of Ag used. Do you guys see how a little bit of a subtle step of adding the word initial or used to these labels will really help clarify things and kind of prevent you from using the wrong numbers in your calculations? If we just wrote through these and you just wrote moles of Ag, moles of Ag, moles of Ag, you would have moles of Ag everywhere. You wouldn't know which one was which. Okay, so just a little bit of extra work will help you get all the way through the problem. So 0.50973 minus 0.24862. Okay, so 0.2611 moles of Ag excess. And if asked for grams, convert it to grams. It probably will be asked for in grams. Okay, that's how we find the excess reactant. A couple more steps after you do a theoretical yield problem. How are we doing? Okay? All right. Percent yield is no big deal. Percent yield is just, it's like a quiz. It's like what you got over what you should have gotten. Right? So percent yield is the experimental yield over the theoretical yield times 100%. Sometimes experimental or actual is used. I like the word experimental better just because it's very clear what the experimental means. But actual can be taken a couple of different ways. Okay, so that's a good place to stop this video. You guys want to say hi to Brooke? Hi, Brooke. Bye, Brooke.